Good morning. For the past 3 months, we've had our Q2 interns at Esri Eastern Africa, and today is their day for presentation. It's been a season of learning, networking, and also getting their hands dirty to be able to work on their projects, and that is why we are here today for their presentation. So it's been a long, short 3 months, and we are really excited to show what we've been working on for the past 3 months. Again, welcome to today's presentation. I would like to usher in the first speaker of the day. That's Agasha Masi. Take it away, Agasha.
Thank you. Morning, everyone. It's an honor to present to you today my project about partial revenue collection system. My name is Agatha Masi. I'm a geomatics engineer and GIS expert. I would like to extend my deepest gratitude to Esri Eastern Africa for providing me with this life-changing opportunity to enhance my technical skills. I also want to thank my supervisors, Jackson, Dennis, Joyce, and the entire Esri team for ensuring that this 3 month period was a success. My study area was Nakawa Division, and it is the largest and biggest area with over 22 parishes. However, for demonstration purposes, I only picked out 8 parishes with the most commercial and mixed land use zones. Now, to understand why this project is so critical, we have to look at the massive revenue leakage currently facing our municipal urban authorities. Traditionally, the government relies on landlords manually filling out paperwork to state what they earn in rent, and as you can imagine, this leads to inaccuracy, and the most honest citizens end up carrying all the tax burdens of those who underreport their earnings. So this project solves these two major problems in tax collection. And the first problem is under declaration of revenue from property owners who report rental values far below the actual reality of the current real estate market. And then the other problem is unregistered properties that are completely invisible to the tax system, like they are not known anywhere. The objectives of this project completely form a chain, and the first objective is to get the teams on ground to map the entire city. Then the second objective runs the spatial engine that uncovers tax gaps. And then my third objective demonstrates a transparent portal that supports planning and decision making through interactive dashboards. So the concept behind my project is actually the hedonic pricing model that was established in 1974, and it states that a property's rental value is determined by its individual characteristics. For example, roads, location, and land use zones. So these are among the strongest predictors of rental income in urban markets. Let me first demonstrate briefly how these factors were used in this project. The first step was to map out buildings from the OpenStreetMap layer across the 8 parishes and obtain their equivalent rent estimates from real estate agents. And then next, The next factor, we know that if your property sits next to a major tarmac road, the rental income generally becomes higher than other structures that don't have accessibility. So I created buffers after classifying out primary roads, secondary and tertiary. So these are the buffers that I created for each primary road, secondary and tertiary roads. Then the third factor, is that if a building is sitting right in the middle of a commercial zone or CBD, its earning potential increases. For example, this deep blue is the CBD. So this structure earns is supposed to earn a lot of revenue compared to the structures this other end in the residential or commercial and use zones. So through spatial joins, I combined all these layers to generate the spatial rent estimates for every structure. And this is where we see the locations of those landlords that are compliant, those that are under declaring their earnings. You can also see buildings that are in wetlands. For example, this is a wetland. So you can also locate buildings that are in the wetlands, buildings that are in the institution zones, and so on. So with this analysis, we are able to also predict parishes that generate the most revenue. For example, with my demo data, here Mutungo generated the highest revenue of about 40 billion, and then Nakawa generated the least of below 10 billion. And there are so many reasons as to why this is producing more and this is producing less. Maybe probably because maybe Nakawa is small, and maybe it has a few structures, depending on the reason. So all these factors are multiplied together to get rent estimate. And to get the tax potential, we simply get the rent estimate multiplied by the number of units of the building, then by 12 months, and by 20%, which is the income tax, and then 75%, which is the occupancy rate. These factors can change depending on what's the percentage of tax. Can be 12%, can be anything. So to my solution architecture, step 1 is the data collection that allows us to gather building details like property owner, declared income, TIN status. And yeah, this is where we find out if the landlord has been paying taxes or not. And then step 2 is the spatial analysis, where we take the field data and combine it with the predictors. And then the predictors that I just demonstrated. And then in step 3, after hosting all the datasets on ArcGIS Online, the data is then used to build interactive dashboards in the Experience Builder. So from here, stakeholders can generate reports for high revenue density parishes. They can also run enforcement plans for unregistered properties and also make other decisions. Then the benefits of this solution. The first benefit is that the government now has evidence to challenge property owners. Then we also uncover hidden properties. So all those hidden properties are now brought into the system. The policymakers now know where much revenue is concentrated, where it is underperforming, and why. So coming to my demo, my entire life cycle of this project is managed through 3 dashboards within ArcGIS Experience Builder. First, we look at our field operators terminal. So the panel cuts Nakawa. So this panel cuts Nakawa into a digital grid system, as we can see from the map, and it is trying to track down all the buildings in that area. So as a supervisor, I can see the completion status of every grid from here. I have a filter, maybe to see the completed grids so far. 430 grids have been completed for the entire study area. Then we can also see work that is still pending. So we have about 454 grids that are still pending. So we can assign more workers or more field workers to actually go back to ground and pick more data or more information. So each grid has a building count. For example, this grid has about only 23 buildings, and then we can assign maybe we can assign this grid to Agasha Masi, and then we say maybe this grid has been assigned, and then we set the priority. If we want buildings in this grid to be high, if we want this work to be completed in the shortest time period, you can set the date that maybe by the end of this month, Mercy should have completed all this work. So this is how we try to track and reduce on the backlog of the work in field. And then the next we move to the revenue intelligence terminal. So across all the parishes with my demo data, the system has predicted that about 190 billion worth of revenue. Like this is the total tax potential that should be generated across all the 8 parishes. However, during data collection, the landlords have declared only about 143 billion worth of revenue. So this is where the government starts to investigate why we are losing out about 51 billion revenue. So from here we can look, we start by looking for the properties that are under declaring, or landlords that are under declaring their income or their rent. So we select parish by parish. For example, Naguru. So every time you select a parish, you're able, it cuts out all the other remaining parish, and now we have one. So we can see that the special estimate is telling us that we are supposed to get 29 billion, but from the landlords, this is what we collected, only 22. And then it means that the government is losing out about 8 billion worth of revenue. So we keep on changing to more parishes and see how the numbers keep on changing. So for example, from our map, Mutungo was the highest. So Mutungo is generating about 53, supposed to generate about 53, but then the landlords have only given us 40 billion which means we are still losing out 14 billion. So this is where we maybe send out more officers to investigate as to why all these landlords are under declaring their rent, or to the third panel, we can actually send out notices to all these landlords. And first we have about 16,000 notices that involve those landlords that are under declaring revenue. So from this table, we can sort out those that are in a critical state. For example, this landlord has only given us 3 million, but then from the special estimate, that this person is actually supposed to give us 18 million. So which means we want to investigate as to why, like, where is all this 14 million? So every time you click on so we can also see the locations. We can see every time we click on each field, the notices keep changing, and also the money, and we keep going to different structures. For example, and the values also keep changing here. So we also want a site whereby these landlords can be able to also interact and see and respond to the messages that are sent to them. So what they do is just note down this reference ID, for example, 5761, and then they come to this survey form that I created, and then 5761, 5761. So you can see that this is where the landlord can be able to verify that actually from this email or SMS that I obtained from the government, this is where they can confirm that this is their structure. So you can see that from here, the same structure that we clicked is the same structure that the landlord is going to see, and then they proceed and fill out, or we can put here maybe a 1, and then we calculate. So every time the landlord inputs their reference ID or property ID, the map is able to show them where their structure is, and they can verify and proceed and complete out the form. Maybe they give the reasons as to why they are only paying 3 million and yet they're supposed to pay about 16 million. So I've already responded to 1. So every time the landlords fill out the survey form, the responses keep increasing onto this panel. Yeah, that's all. Thanks for listening. I would like to invite the next presenter, Richard, to take up the floor. Thank you, everyone.
Good morning, everyone. First and foremost, I would like to appreciate Esri Eastern Africa for this internship. Coming into Esri ecosystem world with just a solid programming knowledge and my experience completely rewired how I think about data. I used to see rows and columns in the database, but through engaging with the Esri Eastern African community and technical resources, and the software stack, I realized that every real world problem, whether urban planning, utility management or tracking resources right here in Uganda is a special problem. Overall, my experience with Esri Eastern Africa has been empowering. They don't just sell the software; they genuinely foster an environment that teaches you how to look at community and industry network and build solutions with a completely new spatial perspective. I thank Madam Joyce, Madam Abigail, and Mr. Jonathan for this opportunity. So back to the project. Ladies and gentlemen, allow me to introduce to you the Petrol Guard system, which is a GIS-based oil spill risk mapping and emergency response system developed to support environmental protection, risk assessment, and emergency response within Uganda's growing petroleum industry. My name is Damulia Richard. I'm a computer scientist and a geospatial engineer with expertise in Python programming, web development, GIS spatial analysis, cloud computing, and database development. My passion lies in combining technology and geospatial intelligence into solving real-world challenges. My project overview is like this. The petroleum industry faces risks as oil spills, pipeline leakages, environmental damage, gas leakages, and delayed emergency response. Using Hoima district as my study area, which is located at the west of Uganda on the shores of Lake Albert, the Petrogad system uses ArcGIS, satellite images, field data collection, and spatial analysis to identify and track high-risk areas, monitor incidents, and support rapid response. The system helps stakeholders make informed decisions and improve environmental protection and also reduce response times. My problem statement is there's a problem of oil spills that threaten the water resources and ecosystems, limited visibility of high-risk pipeline and well locations, delayed emergency response during oil spills, difficulty in estimating environmental and community impact. And then there is a problem of undetected hydrogen sulfide gas, which is a threat to both workers and the community, since this gas is colorless and it is heavier than air. So it lays on the ground. So since this study area is located in the Rift Valley, so we expect that gas to be affecting a lot of people. Then the project objectives to detect and monitor all spills incidents in real time, identify and map high-risk spill zones using GIS analysis, protect environmentally sensitive and populated areas, reduce environmental damage and economic losses, and enhance coordination among the petroleum and emergency stakeholders. Benefits of why this Petrogad matters. There's early detection, cost saving, faster response, environmental safety, community safety, and data-driven planning. ArcGIS capabilities that I used, the ArcGIS Survey 123, where field inspectors would put in data. So we shall be seeing that in the next presentation. And there is the ArcGIS Pro, which is used for analysis and integration. It performs the spatial analysis required to identify risk and response routes. And then we shall be using the ArcGIS dashboard for interactive visualization. This transforms analytical results into interactive visualization that decision makers can make understandable choices. Then we move on to the solution architecture, whereby the ArcGIS Survey 123 will be collecting the locations of wells, pipelines, rivers, wetlands, roads, villages, hospitals, and emergency response units. And then that data will be sent into the ArcGIS Pro, where we shall be doing, or where we did the buffer analysis, the overlay analysis, hotspot analysis, network analysis, etc. That data will be viewed using the dashboard, the APIS dashboard, to track incidents, to know the statistics, and response unit monitoring. This data will be used by POW, NEMA, Petroleum Authority of Uganda, which is POW, UNOC, uh, oil, gas, and companies, emergency responses, government, and communities. So we move on to the survey. Survey 123 will be used by inspectors who got into the field to find these incidents that we are talking about. So we created, there is a field called the incident type, which allows the system to clarify the nature of the event and determine the appropriate response procedures. Here, you can choose maybe a noise spill, hydrogen sulfide leak, a fire outbreak, or etc. And then we have the spill volume, which helps estimate the scale of contamination and contribute directly to the risk level assessment. The value helps to know the risk level or to help in risk level calculations. Then we have the link rate, which helps determine how quickly the situation may worsen and assist in prioritizing the emergency response. Then we also have the distance from the water body. The distance from the water body helps environmental sensitivity and potential contamination risk. There's distance from the community, whereby a near spill can be will be more vulnerable to the community. Then we have the risk score. This field is non-editable. It standardizes the risk assessment by converting the spill volume into numerical risk level indicator. And then we have the date. The date provides information for when the incident is happening or when it happened. So we have the location information. This enables all GIS analysis and spatial decision making within the PetroGuard and location of the device. So we use the location of the device of that who is reporting. Then we have the risk level or severity, which summarizes the overall threat possessed by the incident and support the prioritization. So the inspector will also put in the affected rivers and affected villages. We'll estimate the population at risk to provide a measure of potential human exposure. And then we shall have him or her to make an opinion that we need an emergency response. And then we'll provide an image. He will provide an image for the incident. And then we shall require his name to ensure accountability and enable follow-up where additional information is required. With that, the PetroGuard inspection survey is designed to collect environmental, operational, and human impact information required for risk assessment, risk level calculations, emergency response planning, and decision support. Each field contributes either to an incident classification, environmental analysis, or population exposure assessment or response coordination. Now we move on to the dashboard. Now I would like to demonstrate the dashboard, the PetroGuard dashboard. This dashboard serves as the operational center for the system. At the top point, there are key indicators which shows which well is which. We have the deactivated well, and we have the active wells, which are circled by which are squared into the yellow square. The dashboard displays the total wells, the spill incident locations, exposed water bodies, emergency response routes, emergency response units, populations at risk, um, threat level, pipeline details, and of course the map. So this allows decision makers to immediately understand the current operational situation. We'll start with the oil well, which are these. The oil wells display the number of oil wells in the area. This helps stakeholders understand where the petroleum activities are being centered and where the risk may occur. Then we have the spill location. This shows the number of recorded spills. Each incident can be selected on the map to reveal additional information, and this provides situational awareness and historical context. And then we have the exposed water bodies. These include wetlands, lakes, rivers, streams, etc. One of the most important analyses within the Petrogad is the environment exposure assessment. This system identifies water bodies potentially affected by the oil spills. Currently, the dashboard is showing 83 exposed water bodies. This analysis helps environmental agencies to prioritize protection and measures. Then we have the uh, emergency response units. The Petrogad also identifies the nearest um, emergency response unit. When an incident occurs, the system calculates the most suitable route to, to the affected location. That is done in the ArcGIS Pro. This capability can significantly reduce response time for each incident. Decision makers can identify the nearest ERIUs, route information, and response accessibility. This supports faster and more efficient deployment of emergency responses. So this is the Albertine, maybe North emergency response. And then we have population at risk. Population at risk, it's a capability in the population exposure analysis. For every spill incident, the system estimates the nearby population that could potentially be affected. This information supports evacuation plans, public safety measures, resource allocation, and understanding who is at risk, and etc. So you can see like spill one has people who are affected, who may be affected are over 6,000 people. And then spill 10 has around 10,000 people. In total, people who may be affected are over 27,000. Then we go on to the threat level. The threat level, we have the critical spill, we have low spill. And when I click on it, the spill one is located here on the well. So the threat level on the dashboard also classifies incidents according to the levels, and this enables prioritization rather than just treating every incident equally. Decision makers can focus more attention on the highest risk situation first. Yes. And then we have the route. We have the route. This if a spill happens right now, every minute matters. Who should respond, from where, and by which? So the Petrogad has this routing capability and uses ArcGIS network analysis to identify the nearest ERIU to generate a more efficient route to the incident location. By visualizing the route on the map and the nature of the incident, decision makers can coordinate the emergency operations. And then we have the pipelines. Petrogad also includes pipeline intelligence. The following information is displayed when I tap onto a pipeline. For example, this one. When I tap on it, it brings a pop-up whereby there is a name, a material used, shape, length, diameter, year laid, pressure in, status, and age, pipe age, risk score, and risk level. The risk level is derived from the information collected by the field inspector through the survey 123. The system evaluates several critical factors that are commonly considered in the oil and gas risk management, including the spill magnitude, environmental exposure, human exposure, and infrastructure conditions. The risk score calculation, each factor contributes points to accumulate the risk score on a scale of 1 to 10. We have the spill volume at 3, water affected at 2, and population exposed at 2, pressure 1, and etc. The PetroGuard system applies the risk-based assessment, which is a multi-factor risk assessment model. This is my methodology. Incident data is collected through the survey 123. It's analyzed and predefined in the risk criteria relating to the spill magnitude and environment. So the risk level, the critical level, this approach supports rapid decision making and resource prioritization and more effective to the emergency response planning. So, in conclusion, the PetroGuard demonstrates how the GIS can support safer petroleum operations through risk assessment, environmental monitoring, and emergency response planning. Through the integration of the ArcGIS Survey 123, the ArcGIS Pro, and the ArcGIS dashboard, the system provides complete workflow of the incident reporting, risk assessment, spatial analysis, decision making, etc. By transforming the field data into actionable intelligence, the system supports decision making rather than a reactive response system. So the PetroGuard is not just a mapping application. It is a decision support system designed to protect people, environment, and petroleum infrastructure through the power of geospatial intelligence. So I thank you for your attention, and I would like to invite Wycliffe.
Good morning. Good morning, everyone. I would like to thank the SG Corporation as a whole for giving us the opportunity to learn in close proximity with the software developers themselves. And I would like to thank my supervisors, Madam Abigail and Mr. Matthew Mbiu, for the help they have given me. And also I would like to thank my fellow interns for the collaboration that we had together. And welcome to my presentation. That is profitable niobium zone mining identification in Kwale County. So Kwale sits on one of East Africa's most promising niobium deposits. So this solution aims to it doesn't question whether it exists. It exists since there are geological surveys that have been done to confirm that, and it aims to know where to drill responsibly. So my name is Wycliffe Kipkirui. I'm a GIS intern at ESRI and a graduate from the University of Dedan Kimathi, holding a bachelor's in geoformation science and remote sensing. So my interests are mainly in geospatial AI, machine learning, and the mineral prospectivity. So my problem statement, there is a geological complexity. As we know, the carbonatite hosting niobium is a very hard rock to identify. And there's also the data fragmentation. So my solution uses integrates different data sets to come up with the data-driven solutions. And there's also the high cost and uncertainty. So traditional survey models like going to the field and doing drilling runs, is risky to invest in and also damages the environment. So this is my study area, Kwale County. So my main objective is to identify, evaluate, and prioritize high potential and low risk niobium zones using geological, geophysical, and remote sensing data through application of GIS machine learning to come up with economic, environmental, and social analyses. So my specific objective number one is favorable geology. So my solution aims to identify, in the objective one, to identify the geological conditions favorable niobium mineralization. And also my objective number two is to identify the niobium zones that have the potential for development. And finally, for the specific objective number three is it's lower environmental and social risk through ESG, that is environmental, social, and governance. So this is my solution architecture. I use remote sensing data, geology data, topography, infrastructure, and geophysical data, where pre-processing takes place in ArcGIS Pro. And then after that, I'll run the random forest model for the niobium prospectivity modeling. And then after that, I'll use Topsys to rank the economic ranks of the different niobium zones. And then finally, I will do ASG, that's environmental, social, and governance, to be able to delineate between the niobium zones which are profitable and have posed low risk to the society and to the environment, and the stakeholders that can use this solution are mining companies, the government authorities, the field teams, the public, and the communities. So my solution benefits, there's the cost efficiency. Obviously, first we determine the niobium zones instead of just going drilling blindly. And then there's also the intelligent infrastructure. So we integrate GIS and machine learning to come up with data-driven exploration strategies, and also the protecting the environment through the integration of ESG. And then there's the stakeholder engagement, which strengthen community trust and transparency. So my recommendations are, I would highly recommend we prioritize the first 58 targets and do round routing for those. And then my second recommendation is treat the environmental, social, and governance boundaries as exclusions. It's either we do a buffer of 5,000 to 1,000 meters, or just avoid mining in areas close to these ESG zones. And then so connect dashboard to live results to be able to feed the people on the ground. And then the conclusions are my model was validated, and it provided an accuracy of 96 and an AUC of 98.77, which can be defended. And then there is investment ready target portfolio. So the convergence of highly profitable, high prospectivity, and the ESG compliance will produce 58 immediately actionable tree targets. And the framework is replicable. This framework can be used for other mining workflows in East Africa. And welcome to my demo. So for the niobium prospectivity, I used DEM data, which I used slope to extract the slope and extract the aspect, and the yield shed to extract the yield shed for different azimuths. Since I'll be doing the lineament extraction using this, and for the lineament extraction, I will use edge detection to extract them from the different hillshades, and there is the magnetic favorability. Magnetic favorability. And then there is the gravity favorability, which I reclassified into 5 classes. And then there is the lithology, which shows the areas in blue, which is carbonate. And according to geology for investors, it says that carbonatite hosts 50% of the hosts 50% of the carbonate, which is quite true. The blue region is predominantly carbonate, and also according to geology for investors, when carbonatite withers, it leaves behind traces in circular structures, which are going to be shown mainly by iron oxides, clay alteration, and ferrous minerals, which I'm going to be using to identify the areas within carbonatite signatures. And then after that, I will extract, here is the random forest training models for my study area. I had one occurrence points, which will be the limitation, but I did a buffer of 1 kilometer near Murima Hill to extract the positives for my model. And then I did an exclusion buffer of 3 kilometers from the occurrence points to avoid the negatives mixing with the positives. Then after that, I ran the random forest model, which gave me the niobium prospectivity output, which shows the areas, in green with very low prospectivity, and the areas in red with very high prospectivity. And then after that, I went on to do the economic criteria ranking using TOPSIS. So first, I reclassified my terrain suitability index into 5 classes, and my population suitability index to 5 classes also. For my population suitability index, I'm using it to identify areas with least population density to reduce the cost of compensation to the communities living there. And and I did Euclidean distance, the closest mines, niobium zones to roads, and then distance to water bodies, since the closeness of the niobium zones to water bodies, since mining activities need water for cooling down machines. And also there is distance to power, which electricity is needed to power machines and also to provide electricity maybe at night during the mining activities. And then after that, I ranked these using TOPSIS with the integration of the extracted the very high priority drill targets from the niobium prospectivity. And then so these are the profitable niobium zones, with the areas in red showing highly profitable, with the areas in orange showing profitable, and the areas in green showing moderately profitable. And then after that, I went on to the ESG analysis, where I used, there is the environmental, which I used the tree cover, where I reclassified it into 2 classes. I classified it into classes with region in gray showing very low high ESG risk, and the region in red showing very low ESG risk. And then after that, I did the Euclidean distance to rivers to avoid contamination of rivers by chemicals used in the mining. And then there is the protected areas, mainly game parks and forests, like the Shimba National Reserve. And then there's also the social, which is the population stability, which mainly is in this to avoid the local conflicts with the local communities living in Kwale County. So, and after that, I combined the environmental indices using raster calculator, to come up with an environmental stability index, and also did use data calculator to combine both the population stability index and the environmental stability index to come up with ESG stability classes, which show that the areas in red are areas with high ESG constraints, with the areas in green very highly suitable, and the areas in yellow um, so showing that they requires mitigation. Then after that, I extracted the areas, the niobium zones with high ESG, high ESG, high profit, high prospectivity, highly profitable, and also very low ESG risk. And then after that, I extracted the top 10 deal targets based on the convergence of high prospectivity, highly profitable, and low ESG risk. And these are my top 10. And with most of my view my top 10 ranked drill targets falling within the confirmed RIMA ill occurrence. So this is the dashboard showing the profitable mining identification in Kwale County. So the high priority drill targets extracted from the niobium prospectivity are 345. The prospective zones are extracted from the economic analysis are 324, and the model accuracy shows 96%, which shows that over when 100 of the niobium targets are seen are shown, the model picks identifies 96 either prospective or non-prospective, and the rock is testing the ability to distinguish between the prospective and non-prospective zones. And then in the in the prospectivity analysis, there is a target by prospectivity score. So this ranks the top 10 ranked drill targets based on the random forest probability for niobium prospectivity. So with the IS showing a random forest probability of 0.891242, and then with the list showing among the top 10 0.642600, and then on your right is the random forest importance, which shows that the distance to linear means affected the decision for identifying niobium prospectivity in Kwale County. And also in economic stability analysis, so there is a filter by economic rank, which ranks the top 10, shows the economic rank of the top 10 drill targets. On your right is the niobium target economic ranking, which shows the top 6 scores, which shows among the top 10, with that 5 leading with a top 6 score of 0.85212. And on your right there is the niobium drill target economic profile, which shows the target name, the top C score, economic rank, and then there is a distance to roads, distance to water bodies, and distance to power among the top 10. Then the environmental, social, and governance analysis. On your right is the niobium exclusion coverage. These are the zones that are excluded in in mining for mining targets in the Kwale County, and then on the pie chart shows the niobium target ESG distribution according to the top 10, which shows that 10% of the niobium drill targets fall between the 2.667 ESG score, and then there's a niobium sustainability target profile, which shows the target name, the ESG score, the ESG class. So this shows the ESG classes based on the top 10 drill targets. And finally is the stratified K for the niobium machine learning validation. So there is the stratified K fold where the test dataset is split into 10 K folds, and each is tested on a specific K fold and average and average none. So this shows that 94%, which shows that the model picked 94 targets as real. And then there's the rock or AUC score area under curve, which shows that 98.77%, which shows that there's an eye distinction, my model ability to distinguish between the zones that have niobium and zones that don't have niobium. Then there's a permutation test p-value, which reshuffles my data 100 times to confirm the accuracy, which shows a permutation of 0.0099, which is quite good, and the prior scores of 0.00367. And there's the spatial CV accuracy of 82.91, where our test data set is split into 5 geographical blocks, and each data is tested on one individual block, which is the 5th block, and it yields an average of 82.91, which shows that this is based on geographical zones. And also I like to say drilling blind is versus drilling smart. Thank you. I'd like to welcome the next presenter.
Okay, good morning, everybody. I'm just gonna share my screen. Okay, I hope everybody can see. I'm here to present my project titled GIS-based suitability analysis for telecommunication assets, with the aim of solving telecommunication coverage challenge using spatial data. My name is Kelvin Faustin Lihawala. I'm a Tanzanian. I'm a recent GIS graduate at Ardhi University with interest in geospatial analysis and interest in telecommunication planning and spatial decision support and digital mapping. So the aim of this project is to use GIS and spatial data to solve the telecommunication coverage challenge. The summary of my project is I'll apply the use of weight overlay and machine learning to identify suitable areas by feeding the algorithm suitable criteria for telecom assets. So the outputs I expect include a suitability map and a land cover. For these will show high suitable areas. So as for my problem statement, let's start with the question. Imagine you make a call, then the signal drops, and the internet becomes slow and messages fail to send. Or you're downloading data and the data fails to download. Why does this happen? Often it's because telecommunication assets such as cell towers, they're not located in most effective places. But also there's a lack of a GIS framework to support the placement of decision making. And my study area is Dar es Salaam because it's Tanzania's largest city and one of the fastest growing urban areas in East Africa. The project objectives include identifying optimal location for identifying infrastructure deployment. The suitable location have the aim of solving the time and the cost by reducing the time used in planning, but also the cost used in planning, but also cover the areas needed, but also to identify the spatial factor influencing telecommunication infrastructure placement. Here is where the criteria suitable for the suitability come in, and later on to generate a suitability map from where the decision making will occur. So the benefits of my solution, as I said earlier, to help identify optimal location for improved mobile network coverage, also reduce cost in terms of time and cost for the telecom industry and the investors. Also, enhancing decision making using GIS and remote sensing technologies, since GIS is a technology which helps the stakeholders make a decision by not reaching the site physically. They can just conduct an analysis in the office and make a decision with referencing with the results obtained from GIS. Also providing a scalable framework for future telecom expansion or smart city planning. From this, we are able to expand our telecom infrastructure even in rural areas and other areas which are still haven't been covered, but also improve accessibility and reliability of communication services. This will help making internet connection and mobile connection more strong. Okay, so for the ArcGIS capabilities include ArcGIS Pro. This was used for the spatial analysis and the multi-criteria decision analysis, weighted overlay, data editing, visualization. Also, the Google Earth engine. This was used for large-scale processing. For using this software, you're able to conduct processing of large data. For example, you need classification, the land use land cover classification of the whole Tanzania. This is a suitable software, but also the Google Earth Pro. This is used for the visual inspection. So instead of going directly to the site and costing time and money, we are able to visualize and conduct ground truthing while at the office. And later on, the ArcGIS Online is used for the web maps and dashboard and the presentation of the final results for decision making by the stakeholders. So this is a summary of my workflow. So it involves data collection and the data used, the land use, the roads, existing cell towers, elevation. Also, I had a chance to get data, other data such as airports, military areas, and wetlands. So each layer tells a part of the story. GIS helps to combine them into one decision-making framework. Also, here we come from data processing and preparation. Involves data cleaning, projecting the data to a common coordinate system, but also clipping the data to a suitable area, to a study area, followed by spatial analysis, buffer analysis, depending on the criteria, such as I expect my cell towers to be on a higher ground. So as for the slope, the higher slope will be suitable for me, but also I expect them to be near roads. So 3 to 5 kilometer will be a suitable criteria. But also I have existing towers. So for the 4G network, a 5 kilometer buffer. The 4G network covers a 5 kilometer, so I use the 5 kilometer buffer. But also for the land use, I expect the populated areas, the cell towers to be placed in the populated areas, but also the suitability modeling. This is where I feed the criterias to the algorithm, and I assign weights depending on the importance of each layer. So as for my analysis, for the land use, it had the highest importance because I expect the built up areas, the areas which have higher human activities, they should have the cell towers for increased communication, but also road accessibility was given at 25%, since I expect the towers to be reached in case of maintenance. Also, existing cell towers and elevation was given 20% each. Also, for the validation, here is where the field knowledge from experts, but also Google Earth Pro validation come in, and later on creating the maps, the web maps for the decision making. So here we come to my results. So this is a telecom asset site selection dashboard. This dashboard summarizes the results of the multi-criteria decision analysis used to identify suitable location for establishing telecom assets in Dar es Salaam, particularly cell towers. So at the top cards are the indicators. The first indicator is the total number of suitable sites. It shows approximately 2,000 candidates' locations were identified as suitable telecom infrastructure, and they are marked by the red color. And the total suitable area card shows that the combined area classified as suitable, covers approximately 18 hectares. It means all the suitable areas in my study area have a total area of 18,000 hectares. Also, the last card is the highest suitability score. It represents the most favorable location according to the weighted criteria used in the multi-criteria decision analysis model, making it the highest priority site for deployment. So the best area and the area which I would advise for the telecom and the stakeholders to start establishing the asset, the cell tower, is the area having the score of 1965. I rank the areas depending on scores. So in the time of decision making, they start with the one with the highest score, followed by the one with the least score. Also, the pie chart on the left part, titled Total Suitable Area per District, it illustrates how suitable land is distributed across 3 districts. As you see, Temeke has 75.6%. This is the largest district in Dar es Salaam, and also it has the largest suitable areas. It contains the largest proportion of suitable land, but also indicates that Temeke offers the greatest opportunity for future telecom expansion. It's followed by Kinondoni. It has moderate amount of suitable land. Also, suitable sites there are suitable sites, but are fewer compared to Temeke. And lastly is Ilala. It has the smallest proportion of land, maybe due to limited space or urbanization. Lastly is the bar chart titled Candidate Site by District. It compares number of recommended sites across the district. So here, as you see, there is Temeke. It has the most sites. That's why the total area represented in the pie chart is large. It has sites of has a number of 1,300 sites, followed by Ilala. It has 500 sites, and lastly is Kinondoni. Kinondoni has 200 sites. The pattern corresponds with the suitability analysis shown in the pie chart, confirming that Temeke has the highest potential for telecom infrastructure development. Lastly is the telecom suitability map. It provides spatial distribution of all recommended candidate sites. So as you see, the cycles represent the current cell towers found in my study area. And the red marks are the proposed suitable areas, and the black boundary is the study area together with the district. So candidate sites are clustered mainly in areas where multiple suitability criteria overlaps, such as adequate population coverage, there's good road accessibility, good terrain slope, and proximity to existing telecom infrastructure. So for my project for future improvement, if it's improved, it could incorporate real network data. You can have the real data, the real current cell towers found, the network. We can also incorporate signal propagation models to identify if a tower is placed on this area can cover also it has we can develop a real-time GIS dashboard. Okay. Okay, the question. This is my okay. From this this marks the end of my presentation. Thank you, everyone. I welcome the next presenter, Susan.
Okay, good morning, everyone. Before I start my presentation, indulge me for a minute. I say a quick personal thank you. First and foremost, I want to say thank you to the Almighty, because honestly speaking, there were days I didn't know these things will come up together, but they somehow did. Secondly, every day, every day in this office felt like a dear diary moment, and I mean that in the best way possible, because not a single day did I ever write, "Dear diary, these people are so mean. I need to quit." But it was filled with pages after pages of lessons I learned, people who showed up for me, and moments I never really thought would matter this much. So to the entire Esri team, thank you for the warmth. If Jez was up, I can confidently say that I'm living with at least 3/4 of the pie on my hand, and that's entirely because of how generous you are with sharing what you know. I also want to thank my supervisors, the Miss Latima and Miss Deborah, for there's a long list of things I could say, but one that really matters the most is thank you for believing in me, and thank you for helping me bring my vision into life. That kind of belief is rare, and I don't take it for granted. And of course, Miss Joyce, thank you so much for everything. And hey, Jesus Christ. Okay, sorry about that. And with that, let's get into the Jesus Christ. Okay, sorry about that. And with that, let's get to the presentation. In January 2024, Marsabit County was declared a national health emergency. Camels were dying. Families were losing everything they owned. And the disease causing that Rift Valley fever had been coming for weeks. The rain had fallen, the plains had flooded, the mosquitoes had bred. Every signal was there, but nobody had a system to read the signals in time. And that's what I set out to build. About me, I'm a geospatial professional. Since childhood, I've always wanted to foresee the future and prevent bad things from happening. That's what drives my passion for geospatial. And up until the middle of this internship, I really had no idea how much I loved spatial storytelling, creating awareness through stories and map. That I find that to really sit well with me. And finally, if I'm not solving real world problems or with industry experts, I'm out engaging with my community because I believe that JS is more than just the sense of where. The who is an influential aspect too. Rift Valley fever is not random. It follows rainfall. Every major outbreak in Kenya has been preceded by El Nino flooding. We can see this coming literally from space, but right now, three things are missing. The maps that are existing right now are frozen in 2007 and has no data for today. There's no local precision. The health officer have no idea where to really go. They just do a whole county guess. And next, we are always too late. The response is always too late when the animals are already dying. And 2 million pastoralists in Marsabit, Isolo, and Garissa can't afford for us to be always too late. This project is set out to, one, build a sub-county risk map to tell where risks are, the specific location, spatial location where these rates occur. Number two is to create a live reporting system where community animal health workers can give live updates of what is happening on the ground. And number three is to create a dashboard and an automated system that automatically create tasks and updates when a critical threshold has been a critical threshold has been breached. Number three is to communicate the finding not only to the people that need to respond, but also the community who needs protection from this deadly disease. My solution architecture is consists of 5 connected layers. Number one, data is collected from satellite and from the community animal health workers on the ground. That data is fed into the central hub that is ArcGIS Online, and then is analyzed to a risk model. The risk model is then what drives warn and response, and the results is communicated both to the public and the pastoralist communities that need it. Okay, that's the system, how the system works on paper. And on this is the Rift Valley Fever Alert Kenya County Officer Portal, the entry point for any officer that uses any health officer or vet that uses the system. The first thing that they see is this blue and the red zone. These are hotspot analysis, which are the statistical significant points, clusters of high and low risk that are identified using spatial statistics. The circles with white halos on them, those are the historical outbreak points from the year 2006 to the year to 2024, and they also there is the diamonds. Those are the mosquito breeding sites, and they're live from the community animal health workers on the ground. an officer can tell if there's a larva observed in a breeding site, but either if the diamond is the darkest shade of blue, or if the diamond is the lightest shade of blue, that means that the larva is not present. The squares, those are livelihood location and their health status submitted by a community health worker through field maps. And the triangles with black outlines on them, those are the response tags that the system automatically creates, and they are classified in order of priority. Below the map, an officer is able to get a summary of all the active system layers. They can see what has been monitored, what has been flagged, and the status of all these 3 sub-counties in the study area. This is where decisions get made. At the top, we have these 4 numbers. The highest score across all these 12 sub-counties, which is 3.54, and that is Moyale. And we have 12 confirmed historical outbreak sites from the year 2006 to 2024. We also have an average risk score of 3.03 across all the sub-counties, and the 12 sub-counties are being monitored. Now, the 2 large panels in the middle, these tell their stories on their own. The 16 critical field level with red color, this comes from the community animal health workers on the ground. When a community animal health worker submits a report, the system automatically scores it using a weighted biorisk matrix, sick animals, deaths, abortion, exhibitions of symptoms in human beings, and then it scores it. For a score greater than 12, the system classifies it as critical, and a score that is greater than 7, the system classifies it as a warning. And they are color coded. For critical, for easy analysis, red is they are given color red, and for warning, it's given color orange, like so. Under it, we have this system alert status of 1 with green. This comes from our satellite rainfall classifier. When every Monday, our ArcGIS notebook fetches the CHAPS rainfall data and compares it against the 10 years average rainfall for each sub-county, and then classifies it. Right now, the environment is calm. That's why we are in the normal range. That's why we have the status of 1 in the card. The card is green. But let's say, for example, the anomaly, the comparison from the 10 years and the rainfall for today maybe surpasses, the anomaly is 25 millimeters. The color for this system alert status will not be green, it will be red, and the alert status won't be 1, it will be 4. And Moyale won't be normal anymore. Moyale will be on the alert threshold. Under it, we have the tasks. We have the tasks, 4 pending tasks, and 0 tasks currently being actioned on, and 1 task that is completed. These tasks are automatically created by the system. For example, when these 2 triggers, the survey submission and the rainfall, the data from the CHAPS rainfall, if they pass if an alert threshold or a warning is triggered, the system automatically creates a task, create a task for that sub-county. And the due date is given based on severity. It's the severity of the tasks, and right now we have Moyale. The task status is a priority surveillance, and the priority is high, and the status is still pending. Other than that, a county health officer can also filter by their sub-county, and instantly everything on the map changes. The maps, the list, as you've noticed, the indicators, the everything changes and the charts also changes. So a county officer for Isiolo only sees what is in Isiolo. A county officer for Marsabit only see what is happening in Marsabit and like so. On the next page is the risk maps. This is the core, this is the analytical core of the system. These two risk map, the composite Rift Valley fever risk score, sub-county level risk map on the left, was built on ArcGIS Pro using a weighted sum of 5 satellite variables. The first one is the rainfall anomaly from CHAPS, vegetation greenness from MODIS, elevation from STRM, and livestock density as a population proxy, and health distance to health as a vulnerability measure. On the right hand side, we have this pixel level composite risk surface. This is what the sub-county risk map on the left was aggregated from it, and on it the historical outbreak points are overlaid. And from these, you can see that almost all the historical outbreak points fall on the red or the orange areas. These are the high and the very high risk areas. And that's the validation of our model. This is the first view. And on the second view, we have the hotspot analysis map, which is a significant statistic clusters of high and low risk zone. Low risk zone identified using spatial statistics. On this page, the third page, this page tells us what is actually happening on the ground. A community animal health worker, those are the pastoralists, so they are community volunteers. They fill this form on their phone, and it can be entirely offline for those remote sub-counties that are hours away from a network signal. The form contains 7 epidemiological indicators. Number 1, the sick animals. We have deaths, we have abortions, we have symptoms in human beings, we have proximity to flooding, and presence of any recent rainfall in the area. When a community animal health worker clicks submit, the form is the system automatically calculates the scores, the response using the weighted logic I explained in the situation room, on the situation room dashboard earlier. And on the right hand side, we have the recent field submission. These are submissions that drove the 16 critical that you saw on the dashboard earlier. Everything on the 4 previous pages detected, and here is where actions are made. The reference alert threshold on the right hand side tells an officer what each risk level means and what they should do if the risk level is surpassed. 4-step standard operating procedures when a warning or an alert has been triggered. Below is their emergency contact lines for all the county director, vet directors, and also for the Kenya Zoonotic Disease Unit. And now, below the map, we have the task. These tasks are created with two triggers that run first on the rainfall data. When an alert or a warning has been triggered on the rainfall data that is fetched from CHAPS, as I said earlier, the system checks first if there's an existing tasks for that sub-county. And if it's not, it creates one for it to avoid duplicates. And the second one is the second trigger runs on survey 1 to 3. If after the biorisk is recalculated, the system checks if the survey is on scores a warning or a critical. Then it again checks if there's a pending task for that sub-county. And then if there's no pending task, the system again create task for that sub-county. Now, so far, everything that you've seen is for the county officers or the technical people. But then what about the community, the pastoralists who do not understand or do not know about JS? There's also a website for them. This is the Rift Valley, Kenya public website for the pastoralists in Marsabit, Isolo, and Garissa. They get to know what Rift Valley fever is, and they get to see if their sub-county is at a risk level or not. And also they get to get measures on how they can protect themselves on if again this disease strikes. For example, because Rift Valley is zoonotic, it can be transmitted from animal to human. They get to know what to do when there's an outbreak. They avoid handling sick animals. They avoid grazing near flooding areas. They avoid drinking raw milk, and then they report if they see something. They can also use the survey form that I showed earlier to report what they are seeing. And they can also read the full stories on story maps, and health officers also can use this website to log into their website. What changes when this system exists? First thing, the pastoralist gets weeks of warning before, rather than just days of reacting to the disease that is all at the time killing their herds. The second thing, the disease is not thinly distributed across the whole county, but the officers, the health, know where exactly to take the vaccine. For example, if there's an outbreak maybe in Moyale, they know that this specific village in Moyale, that's where the outbreak is. That's where we should concentrate on while vaccinating. The second thing, as you know, that the pastoralists, their income of their livelihood depend mostly on their herds. And with this system, with early warnings, their livelihood is protected, and the economy of Kenya will grow. And this system is built to grow nationally. On the previous studies, it is shown that in Kenya there are 22 areas which are Rift Valley fever high risk. So with this system can be scaled to help also those counties. And now to the recommendation and conclusion. This system should, I recommend the system to use ArcGIS velocity for the phase 2 automation. Rather than just collecting data from weekly satellite data, the system can update daily live updates on this rainfall data. The second one, I recommend the system to be scaled on those 22 sub-counties, that the 22 counties that are at high risk of Rift Valley fever. The third one, I recommend this system to be handed over to the county Ministry of Health, or the counties that are at risks of those of the Rift Valley fever. And to the conclusion, Rift Valley fever will come again. El Nino is not going anywhere. Flooding is not going anywhere. But the next time those rainfalls on Marsabit sub-county, we won't be caught off guarded. We have a system now. Thank you. Now to the next presenter, Alnayan.
au anashare kwenye entire window na boy. My name is Alnayan Al-Bashir. My name is Alnayan Al-Bashir. First of all, thank you to Esri Eastern Africa for this opportunity, giving us the time and good management so as we can explore and expand in the knowledge on geographical information system. Thank you to our supervisors. Thank you to Grace from Esri Eastern Africa. Thank you to Adija in Tanzania office for showing the cooperation to us as Team Tanzania. Thank you to Christine Chege, my supervisor, for assistance from the start to the end of this internship. My project title is Smart Road User System, that is leveraging GIS and IoT for intelligent transport system for efficient urban mobility in Dar es Salaam City, Tanzania. My name is Alnayan Al-Bashir. I'm a software engineer, but with a background in business information technology from the University of Dar es Salaam, Tanzania. I'm currently specialized in software development, designing the scalable solution and implementing the real-world solution to the challenge that exists for ensuring the real challenge that face our community is solved for the better life in our society. The summary of my project: in Dar es Salaam City in Tanzania, the government is struggling for ensuring that due to the most of the people travel from rural area to urban area searching for employment opportunities. So this lead to increased depopulation growth in Dar es Salaam City. But due to the presence of limited infrastructure, and as we know, with the rule of economics, when we have limited resources, we need to find the way in such a way that we can utilize the resource we have and ensure the maximum productivity. So with the question, when we have limited infrastructure and we can't expand them more because we have limited land and we need to produce in other sector, like in other business production. So maintaining the present infrastructure, we need to utilize them well so that we can make sure that the productivity is improving, but the transportation system is still better. Is now we come up with improving the technology that will enable to use the present, to use our available roads and infrastructure for the better use without expanding them more. The problem statement is that in the lesson we experience traffic congestion, limited load accident, incidents, visibility, and analysis due to the absence of real-time data on what is occurring in the road, delayed emergency response due to the absence of real-time update from the users of the roads. The study area is Dar es Salaam City, consisting of 5 main districts: Kinondoni, Ubungo, Temeke, Ilala, and Kigamboni. That's is connected with almost 15 main roads, including Bagamoyo Road, Morogoro Road, Nyerere Road, Hassan Mwinyi Road, and the other roads. The objective of this project is to enable real-time road updates by enabling the road incident to be reported, road incident analysis by the traffic officer and the government authority through this platform, and enabling GIS decision support so that to respond on the incidents once they occur. The benefits, what we intend to get from this solution is fast emergency response, like when floods occur, accidents, and other incidents, so they can be attended immediately, so as to avoid traffic congestions, reduce traffic congestion, smart transport analytics in our roads, better decision making due to the presence of real-time data in our system, efficient transport management, and improve road safety for the road users. The JS capability that has been utilized in this project is ArcGIS Map SDK software development kit for JavaScript, JS Online for authentication of maps integration and these layers, ArcGIS dashboard, geoanalysis, spatial processing for the data for spatial data, and web map for incidents display in our web app. That is the solution architecture, and the tech stack that will be used is I will use the React.js, Node.js, MongoDB, Socket.io for real-time updates, MongoDB for spatial data storage, and ArcGIS Orani for authentication. We have almost 5 layers in our architecture: data source, that's a data layer, data storage, data processing, and the web client for data access, and ArcGIS Online for multi-factor authentication. Data will be collected from IoT sensors combined with cameras that will be inserted on the load junctions. So when the incident is detected, like high-speed driving, the camera will take the event 30 minutes before and 30 seconds before and 30 seconds after the detection, so as to report this incident in the system. We will use the vehicle GPS so as to detect the vehicle density in loads and track their location. Mobile reports by reporting incidents from road users like vehicle owners and the traffic officers reporting violation and emergencies. Open data and external APIs that will be stored in MongoDB. The road network, traffic sensors, and incidents and geo indexes will be stored in the database. The data will be processed at the back end, and the authorized authentication will be performed with the business logics. Data will be viewed through the interactive map in mobile and desktop. Normal user will use mobile phones for the mobile application and the websites, but the government authorities will use the extended software. Will use the extended desktop to access this platform, the website, and we authorize the data through, we authorize the API through multi-factor authentication. Our stakeholder will be traffic operators. They're operating operating the load and checking the load in real time in their office, RATRA officers, turn load for load improvement, city planners, law enforcement like traffic police, emergency services. When accident occur, we need ambulance for checking the people in the hospital, and the public citizen use the loads, but the data will be visualized in the live traffic map, congestion heat map, incident alert, graphics, and now let's dive in the little demo of my platform. This is the user site. A user site will see the incidents. Incidents are categorized in the main incident that occur on the road, like road accident, traffic congestion, vehicle breakdown, road blockage, road construction, and the flooded areas. So these are incidents that are occurring in the road. Some of incidents are used so as The platform will be using real-time data, so I generated the auto data for demonstration, but I added my own data directly from this software for demonstration. Let's say the incident has been reported almost 1 hour ago. There is a flooded road at Bagamoyo Road. Now you can open the map, you can open the event to see in the map where this event has occurred. The incidents in around this area in Bagamoyo Road, there is a flood, and to show the impact of this platform, the difference from this and from using the Google map, we have the support of the videos and image, even audio, for the person who has uploaded this information. You can see the area, like the condition of the road is like this. So the user of the road, they can see that, is this way possible right now, or should I change the direction so I reach my destination, so to avoid increasing the congestion of vehicle in this area. So you can see this is like the road is like this. So the road user can see that this road is like now Bagamoyo road is not passable. So we have to change the way so that we can reach the destination. But also the user can view the whole map, seeing the incidences that you're carrying in the road. This is the map showing Dar es Salaam city, what is happening, and this is the region to show. This indicates flooded road, dangerous driving as detected, security incident, vehicle breakdown, road blockage, failure, fallen trees, traffic congestion, and others. So we use the key to determine this mark, what they do indicate. So, but you can filter, this is the accident occurring in these areas. You can filter to see the congestion area. These areas have high congestion right now. But also a user when wants to report the incident, he has to come here, the page. He can report incidents, select which kind of incidents, write the title, description of event, set the city Dar es Salaam, and set other things. You can choose the exact position by clicking. It will take the coordinate of the point, or you can use the GPS to detect the area when are you reporting from. Let's say you are on the rail station, you can auto detect by clicking on the GPS track. So once this is reported, we come to the officer, to the traffic officer. This is the page. This is the officer location. As you see right here, the officer location is right here. This is my position as I log in as a traffic officer. So a traffic officer will be able to see the incidents nearby his area. These are incidents nearby his area, so he can see and attend them in real time, so that he can reduce the congestion to resolve these issues. Like when an accident occurs in the road, traffic need to go there, inspect and determine who is the troublemaker, so as can write the fine, and then the load which can be resolved, and the other thing may proceed. So during this time, nothing should be altered in the load, so as a traffic officer can take the evidence. So they need to attend them instantly through real-time update, so that they can resolve the issues. You can detect the nearby. So when you click nearby, you can see nearby event is right here. So you can see the nearby event. You can see, let's say this is an event. You can see the detail. You can see the details by clicking right here. This is a nearby event, and this is the latest incident reported. You can click to view. You can view the event, the situation right here. There is a flood, and there's image, supportive image uploaded over here. You can see them, and go to the situation. But also, when the incident reported is marked as high, has a high severity, they come to the emergency area. So if the incident has a high severity, so it is it come automatically to the emergency dispatch area, so that they can be early determined by the traffic officer and attend to them. So when he select to find their routes, so you can see that this is the routes, the shortest police station. Let's say this, if it's grab like a road accident or other events, the nearest police station that can come to the situation is from here. It seems that it is 5 meter. It's 5 minutes to leave the area. It is 2 kilometers via Old Bagamoyo Road. So let's give the information clear. So this police station is the one will be responsible to attend to this area, because this is the police station near to the events. And then when we come to the violation, there's a violation, let's say wrong parking, long parking and whatever. So you can see these are violations that are reported in the area. So the traffic officer can select a certain violation so that he can see where this violation has occurred. Violations are occurred over here, the wrong parking. So this wrong parking also can cause congestion. So he can go quickly to attend so as to resolve this issue, so as to avoid this situation. Maintenance area, when there is, let's say, blockage roads or there is any incidents, these are reported by traffic officers themselves, that certain area is blockage, and then will be viewed by the system administrator of the government authority, so as he can find the way to resolve this issue, so as to ensure that the roads are in the safe condition. Now, when we come to the government authority like RATRA, this is the system admin panel, we can continue with this incidents, like when the maintenance things are reported, he need to approve. Come here, let's say this, he has to approve. Now, when he approved, it means the problem has started to be worked on, and then the issue will be resolved in a short time, and the load will stay in the safe condition. Now let's go to the GIS operation for this system. This will be the dashboard that will be showing the map of Dar es Salaam city, showing that now we have total, there's a active incidents right now. We have incident report today is the one I reported, and it is critical. Now it needs to be resolved. And we have 21 other critical issues. Resolved is 17. We have almost 35 roads that we have dealing with right now. We have sensors and 14 sensors and 40 sensors and 40 cameras, and the 10 stations in Dar es Salaam city. So now we'll be having different operation. Like this is an overview, but when we want to get the details, there's a sensor status like 29 are active, with default are 60, they need maintenance are 5, road condition fair 15, poor 60, and the whatever. Top violation, mega parking 15. So this will be showing the overview of the load condition, and the authority will be able to catch up the information lead time, and they can improve and make this issue resolved, making the road in Dar es Salaam better. But when we come right here, you can see the district Intel. We have 5 districts. Kigamboni is in a risky. and this risk is determined by the road congestion and accident. So Kigamboni, the risk score is 34, it's the high, but Ilala, it has a risk score of 10, Kinondoni 10, Temeke, it's 10 also, and the Ubongo, it's 10. But when you want to see the real condition of the area, you can click right here to see. In Ubongo, here is the Ubongo, this Ubongo interchange. So you can see the area. In the road, there is no, in this main road, there's no congestion, just why you see the risk score is 10, it's low. So the road is safe. The area around the Ubongo district is safe. So the car flow is well in vehicle. So it's clear. But when you come to the traffic, you can see the traffic by day, traffic on Sunday, it was on this late to Saturday, like this. You can see the average response time to the incidents when they occur is 2.5 hours. So within 2.5 hours from when the incident is reported, the incidents are reported, attended and being resolved. But there's a peak hour when the road have more congestion. But right here we have the data to download, loads the incident sensor and whatever. This maybe they are in the GeoJSON format, so they can be used in more analysis. The road safety, you can see the road safety like total accident, injuries, fatalities, the weather conditions like this, rain, fog, rain. These are the infrastructure, performance, signal status, congestion index, like this, road score risky. Each road is now, this is a road score risky. Kibamba has a score risky of 41, as a score you can see, and the Mbezi road, it has 1/100 risky. Emergence coverage. This is the emergence coverage. Predictive trends. Now you can predict what will be happening, let's say by using based on the last 14 days of the sensor history, 4 of the next 24 hours are projected to reach heavy, severe congestion. So by using the previous data, we can determine the upcoming congestion in the certain area. But in the spatial analysis, we have 4 spatial analysis. We have buffer analysis, proximity analysis, density hotspot, and the road corridor impact. On the buffer analysis, we can check like in the around a certain area, how many incidents are there. Now I use the Secra buffer analysis. Now I have to pick the location. Let's say right here. And I have to set the radius since I use the Secra buffer. I want to perform the buffer analysis on the area selected, but in around the 2.4 kilometer in all direction. And then when I click right here to perform analysis on this area, now let's check the information. Buffer analysis of 2.3 kilometer in radius found 8 incidents within 2.4 kilometer of the selected point. And these are more details about this buffer analysis. So we'll be able to determine the incidents that are occurring in this area by performing buffer analysis, Secra buffer analysis on a certain area. But proximity analysis to see from a certain distance from this area, how many incidents are here. Now we have to change. Now let me select right here on this point so that I can determine. Now information say that proximity analysis nearest 5 incident, closest closest incidents, and then there is the density hotspots. You can perform density hotspots to determine the density. We have 43 incidents grouped in 43 spatial clusters in these areas, route corridors. So all these are part of analysis you can perform in GIS. Now in the part of analysis, this will be showing the dashboard and the graphical interface by category, medium, critical, and other more monthly trend of the incident in the load, the category of category breakdown like road construction, 7, 4, and the other more. Spatial analysis based on the time. This is the graphical. Traffic analysis. You can perform the traffic analysis. This is the trend of how congestion in the load. And these are risks, traffic daily by week. Load surface. Now you can determine the load surface. These are incidents caused by the road condition by categories. This caused by weather, incidents caused by the road condition. Congestion prediction. As is. No, due to time, I just went faster so that I can count or score, but there's a lot of things to explore. So just why I touched few of criteria that is just based, so that the other things are very important, but due to time, I have to end up my presentation here so that other presenter can proceed. Thank you. This will mark the end of my presentation. Thank you for paying the attention.